All right, guys, this is going to be the moment of inertia derivations with calculus. I'm going to derive a couple for you, show you how to do them in general, and go over a couple of free response problems that apply to this. This will probably be part one because I think it'll probably take a little bit to go through all the steps. So in general, we learned that generically our moment of inertia was equal to mr squared. And if we have an axis that isn't changing, which would be what this point is, we can find out what this is with an integral, taking into account how far I am from this position that's going to be the axis, and have little parts of mass, which we're going to call dm. So the smallest amount of mass. And so on your equation sheet, they tell you that the moment of inertia, which is going to be similar to mass, so not how hard it is to accelerate something in one direction, it's going to be how hard it is to rotate something, of r squared dm, the integral of r squared dm. All right, so I know that my moment of inertia is going to be equal to my integral of r squared dm. Now, the problem with this is that we have a different variable and a different thing we have the derivative of. So we need to make them the same so we can actually do the integral. And so if I look at what this is, and I'm going to say that the mass of the ring has no dependence on r. So very, very thin hoop. What's the moment of inertia? You might know what this is just from remembering that it's just mr squared, but we want to derive it. Okay, so I can say that the ratio of dm over the total mass would be the same as the ratio of d theta over the total theta. So d theta would be this tiny little angle measure, and theta would be one time around. So this one time around is going to be 2 pi. All right, so let's see what dm is. So dm is going to be equal to m over 2 pi d theta. And when I put this up and substitute this in for dm, I get that I have the integral of mr squared over 2 pi d theta. Let's move everything out that is a constant. And what we're left with is mr squared over 2 pi integral of d theta. So all we have is this from 0 to 2 pi. And so this is going to give me mr squared over 2 pi. I have theta from 0 to 2 pi. And so I'm going to have 2 pi mr squared over 2 pi minus 0. And we get what we started with, which was I equals mr squared. We're saying that it has no dependence on the radius. So that's a constant because it was always the same distance. And this would be about its center. So again, we can relate this dm over m to a length or a distance. So that could be dl over l or dx over x. It can also be related to an area, which I'll do for the next one. So dm over m can be related to the dA over A. Or in 3 dimensions, it could be dm over m is related to dv over v, where v is the volume. And these ratios are going to hold true for things that are uniform. And that's what we would be finding. A lot of times it's different places about a rod, which is what I'll end with you. All right, so that's just the example, and it is explained, which I just did for you. All right, this is out of order, right? Yeah, because it's the disk we're seeing about center was the next one. So I'm going to start with what I had, which was I equals mr squared. And I'm going to think about what my disk is. And I'm going to think about my disk as being a bunch of these individual hoops just piled on each other. So they're going to be a distance, a certain distance away. We'll call the distance from here r. And we're going to take the distance from any hoop that we do that we're going to build into this disk is going to be little r. And so I can say that dm over the total mass would be related to this area, which would be dA over the total area. And so I'm going to call this tiny little thickness of this hoop that I drew dr, the change in r. Remember, little r is how far away we are. So I'm going to have dm over the total mass is going to be dA. And so the total area of this is going to be the circumference around, which is going to be 2 pi r, times the thickness, which is dr. And again, this is little r because it's an arbitrary point between 0 and how far out you go. And I'm going to put this over the total area of this disk. And the total area of this disk is going to be pi r squared, because big R is how far out the disk goes. So we're going to integrate from 0 to r. And so I'm saying that this is the integral of r squared dm, and we're going to go from 0 out to r. All right, so I can cancel stuff. Not a lot, but I can cancel out pi, and I can solve this for dm. And I can say that dm is equal to m times 2r dr over r squared. So I'm going to plug this into my integral. And so I'm going to have the integral from 0 to r of 2m r times r squared dr over capital R squared. And again, the difference between capital R and little r is going to be what we're going as we go out, each individual distance. Capital R is going to be the end of our, how far we're going to go out to. So I'm going to take out everything that's not going to change. So I'm going to have 2 capital M over r squared, integrate from 0 to r of r cubed dr. And so when I take the integral of this, I'm going to have 2m r squared. This is going to be r to the 4th over 4 from 0 to r. And our 0 is just going to be a 0, right? So when I plug in my capital R, I have 2m capital R to the 4th power over R squared over 4. I can cancel out R squared, and I can cancel out 2. And so this is the derivation of a disk. And it's 1/2 mr squared, which is what we found it was. All right, let's go back because this is the order that it is in your notes. Now we're going to look at a rod that is rotating about its end. So there's my axis, and when we do a rod, we call how far it goes L. And so I'm going to start with my generic integral, which is going to be R squared dm. So R squared dm. And again, I'm going to say this is uniform. So there's going to be a ratio that dm over the total mass is going to be related how far I am away from the axis, dx over x. So let's solve this, and I'm going to say that dm is m dx over x. And in this case, our x is a specific x, which is L. So let me rewrite that actually as L. Right? Because we're saying that that's the actual length of the rod. And again, R, L, and X are all measuring the same things in this case. So I'm going to substitute dm in here, and I'm going to get that I have the integral from 0 to L. So I'm starting at the axis and going to an L distance away of m over L R squared dx. And really, like, R is a generic distance 1 as well, so I'm going to make those x squared. Or I could make it R squared dr. It doesn't matter. I want it to be the same. So I'm going to take out what is constant. And when I do my integral, I'm going to get m over L. I'm going to get x cubed over 3 from 0 to L. And so I'm going to have ml cubed over 3L minus 0. And it looks like the moment of inertia is ml squared over 3, which I know it to be. All right, I'll show you with calculus how to do the middle one as well, and I'll show you with calculus a little bit later in this how to do anywhere in there. But if you know what the middle one is or the end one, we have another way to do it, which is called the parallel axis theorem, which I'll show you guys as well in a different set of notes. All right, so now we're going to do the same thing. But now we're rotating it about its center. And you might know what this is. You might remember. You might not. But again, our integral, R squared dm. And I'm going to say that dm is to the total mass. Why don't I call it dr is to the total length. And that way it's agreeable with what R squared is over here. I'm going to solve for dm, and you're probably thinking to yourself, he's going to get the same answer. When I substitute this in for dm, I'm going to have m over L R squared dr. So what changed? What's different? The difference is what we're integrating from. So if we're saying that this is our axis, this is 0. And so I'm going to integrate from negative L over 2 to L over 2. So this distance would be negative L over 2. This distance would be L over 2, which was different from 0 to L. And you can see where if you move this, the only thing that's going to change is what you integrate over, and it's going to give you different moments of inertia based on where your axis is in this uniform rod. All right, so let's take the M over L out. And I'm going to get M over L times R cubed over 3. And then I have negative L over 2 and positive L over 2. Okay, so I'm going to have M over L. I want that to be a little bit darker. I have M over L. And then I have L over 2 cubed over 3. So that's going to be L cubed on the top. 2 cubed would be 8. And 8 times 3 would be 24. So I have L cubed over 24 minus. Now, this negative L over 2, when it's cubed, it's going to be a negative value as well. And so this is going to end up being negative L over cubed 24. All right, so when I add these together inside of here, I'm going to have 2 L cubed over 24 M over L. I can get rid of 1 L. So my cube to become a squared, I can get rid of a 2, so this will become a 12. And so I would say that the moment of inertia, spinning something about the center, is 1/12 ml squared. And that is what it is. Or that's what the value is. I did that one already. And here is a longer, different explanation for the disk, which you guys have in the notes. All right, I'm going to stop here because we're going to have to both get the moment of inertia of this with calculus and then get its period with calculus. So it's going to be a rather lengthy process. So that'll be part 2 of the derivation.